Good. So now we know how to rotate the qubit state using precession about the z-axis. We use it to build the z gate, the s gate, the t gate, right? But we also know that, if you remember, any quantum gate can be decomposed into a rotation about the z-axis, and then about a horizontal axis, which is y-axis, and then about the z-axis again. Now, so it is very important to be able to bring a state from the top to bottom. How do we do this? Now, in principle, you can say, well, I just pick up very big magnetic field horizontally, right? Then isn't that then you will precess across about this axis? And that is true. But this is not flexible, because the magnetic field usually is high and you don't want to rotate it so often, right? Even not for quantum computing in the old time, for magnetic resonance, nuclear magnetic resonance, right? So here we just have this, and another idea is to, in addition to this external magnetic field pointing in the z direction, we're going to apply a AC magnetic field in the x direction, with the field being very small. So it's small, so we can change it easily. And at the same time, we try to oscillate it at the normal frequency to get something called magnetic, something called spin resonance. Okay, so we'll study this eventually, right? But just take it for granted for now. We are going to have a large external magnetic field pointing vertically in the positive z direction, and then we will have a small magnetic field oscillating at a frequency called omega-1, not yet at the normal frequency yet. We want to use it normal frequency, but let's just generally call it omega-1, so it is oscillating. Okay, so let's look at this physical problem. When I have the magnetic field pointing up with B1, B0, and if I just call it B0, this is DC, right? I'm going to also add the Z hat to it, okay? So that this is the magnetic field, right? At the same time, I have the AC part, which is B1 in the X direction. So how do I describe the total magnetic field? The total magnetic field, of course, equals to the X component, B1 cosine omega-1t X hat plus B0 Z hat, right? That is the total magnetic field, right? So how about the interaction Hamiltonian then? The physics is the same, right? So the Hamiltonian must be negative mu dot B, okay? But how about what is the mu that I should use, okay? So the mu, in this case, the mu is equals to the gyromagnetic ratio, which is E divided by M, right? This is the gyromagnetic ratio times the spin. And because the gyromagnetic ratio, the spin and the angular momentum supposed to be negative of each other, so I'm going to put the negative here, right? So I also got confused a little bit with my cheat sheet, but just want to show you this. What is the magnetic moment? Mu equals to the gyromagnetic ratio times the spin. And this gyromagnetic ratio is negative E over M because I just assume G equal to 2, right? That's why I have this one, right? Now, that's why we did the spin operator. Now, if you do this, then what do you get? E over M. And then what is the spin? Look at here. This is the spin angular momentum. Sorry, I keep saying the wrong thing. This is the spin angular momentum, not spin, right? Spin angular momentum. What is this? This is equals to h bar divided by 2. And I'm just going to write in the row form, sigma x, sigma y, sigma z. Dot product with the B. What is B? B1 cosine omega 1t 0 and B0. Right. If this looks confusing to you, then I can do it in this way. This is equals to what? E over M h bar over 2. H bar over 2 is because of this. H bar over 2, right? With times sigma. And what is sigma? Sigma x, x hat, plus sigma y, y hat, plus sigma z, z hat. Dot product with bx, x hat, plus by, y hat, plus bz, z hat. That is exactly what I'm talking about, right? Mu dot b, the magnetic moment, I now convert it into the spin. So it is negative E divided by M times S, which I have this one, right? And then dot B, which is this one, right? Any 3D vector is like this. Here, what I'm doing is just putting into row and column so I can do dot product easily, right? Sigma x, sigma y, sigma z times Bx is what? B1 cosine omega 1. By is nothing, 0. Bc is this one, 0, right? So if I do the multiplication, what do I get? First, I get the first term due to the x term. So it is b e over m h bar over 2 times b1 cosine omega 1t, the whole thing times sigma, right? And then plus the second term, e divided by m, h bar divided by 2, b0 times sigma z. Okay? Now, you see this thing. If you see that the Hamiltonian now has one term which I will call it h0, the original Hamiltonian. And then I call this term as hi. This is the perturbation. This is like a perturbation. A very small term to my original system. Right? So the whole thing is that the Hamiltonian is equal to hi plus h0. Now, what is h0? Let's look at it carefully. It's just b0 times e divided by m times h bar divided by 2. This was the Hamiltonian of this one. Right? This is exactly the same as that one. Because the mu, what you saw there is HAE divided by m h bar divided by 2, right? As I show you here, this is the mu, E h bar divided by 2m. Okay? So this system is just like that. It's the same system we have studied before for the Larmor precession, except that we add a new Hamiltonian, a new perturbation to this Hamiltonian. Okay? And so then we will use the perturbation method to solve this problem. Okay? So this is the first setup. Now, so if this is the case, then let's discuss a little bit more H0 plus a perturbation. Then what our goal is this, we want to try to represent the state with perturbation as a linear combination of the basis vector without perturbation. So what does it mean? Let's look at this. Now, for only B0, I mean H0, right? When you only have the original magnetic field pointing in the H direction, in the Z direction, you have H0 equal to B0 E H bar divided by 2m sigma Z, right? I just copy from here. Where? Here, right? This is the original Hamiltonian. And we already know that. What does that mean? That means that it has the eigenstates or eigenvectors of 0 and 1. Because this one corresponds to the magnetic field pointing up in the Z direction. So their eigenstate are 0 and 1. Okay? So as the time goes by, how does it evolve? Right? So at time t, 0 is going to be equal to the initial 0 times e to the power negative I energy. This is the energy of 0 divided by h bar t. So this is a general quantum mechanics result, because you will find that you substitute this into the Schrodinger equation, it will satisfy, and E is the eigenenergy of that state, right? So what is the E here? If you remember at the beginning, I show you that when you apply a magnetic field in the Z direction, you actually reduce this by mu B times B0. Okay? So here, actually, I think I need to change this. Yeah, I know this is confusing. The problem is actually 0 is the excited state, right, in our framework. So 0 equals to spin up equals to the excited state, right? And because of this, actually E0 is this one. Okay, so you are increasing the energy. So it is not negative, it is mu B, B0. Okay, so I said it wrong. So this is equals to 0 e to the power negative I mu B divided by h bar t. Okay, but what is mu B divided by h bar? This is equals to 0 e to the power negative I. You probably see it already, but I try to expand it, right? So this becomes, instead of B, you put B0. This will becomes E h bar divided by 2m. That is mu B0 divided by h bar t, right? E B0 divided by m is just the Larmor frequency. E to the power negative I omega L divided by 2t, right? Because h bar got cancelled, EB divided by m is omega L divided by 0. Now, actually, this is very simple. You don't need to go here. You can even just use this equation. By looking at this, you see that as the time goes by, the phase of 0 increased by 2 mu b divided by 2. Remember, you have a 2 here, right? Divided by hb. You will get the same result. Okay. Similarly, for the one state, which is the ground state, okay, is going to evolve as negative, as I omega L divided by 2t. Instead of negative, it becomes positive because it has a negative I, but the energy is negative because now it is a ground state, you reduce by mu b. Okay. Sorry for confusing you, but hopefully you understand what I mean, right? The first thing is that for the original Hamiltonian, I have some ground state and also this is excited state and ground states. I have two states, that is eigenstate. Under this Hamiltonian, the eigenstate does change, but only change by a phase, e to the power I eigenenergy divided by h bar t. This is what we learn in quantum mechanics. If you don't know this, fine, not a problem here, right? But it's good to learn now. Just say, okay, it's equal to any state, right? Let me say again, right? If you have an eigenstate, let's say lambda, right? At time t, it's just equal to the initial lambda times e to the power negative I lambda divided by h bar t. If lambda is the eigenstate of the Hamiltonian and lambda is the n eigenenergy, right? So this is the eigenenergy, right? I should say this. E0 is the eigenenergy of state 0. And similar, E1 is the eigenenergy of E1. And from quantum mechanics, we know this is true, right? If you don't like this, you can also use this Lamarck precession equation to find out that in D, it is going to evolve in this way, because this turned out to be its eigenenergy. Okay. Now, so what is the point of doing this? Now, because this is a perturbation, right? By adding a perturbation, with hi equals to b1 cosine omega 1t e divided by m right, h bar divided by 2 sigma x. This is the perturbation we add to the original system, okay? We can model a general state. Okay, now this state is in this new system in h0 plus h1 equal to h. In this new total Hamiltonian system as a linear combination of 0 and 1. Zero at t and 1 at t. Okay, so what I mean, psi of t is going to be equal to 0, 0 of 0 e to the power negative I omega L divided by 2t. Okay, because 0 times e to the power omega L divided by 2 is exactly the state of the excited state at time t, right? Plus C1 1 e to the power I omega L divided by 2t. Okay, and the condition, of course, is we need C0 square plus C1 square equal to 1, so that you have the same, so that you have the normalized probability, right? Do you see this? So in summary, I just model any general state as a linear combination of the basis state. But this basis state, I don't just put 0 and 1. I also spell out that it actually has a phase keep changing with t due to this original Hamiltonian h0. So this is the wave function when I add a perturbation to the system. Okay? So we have the wave function. We have the Hamiltonian. And what we need to do is to solve the Schrodinger equation. How do we solve it? I h bar partial psi partial t, right? This psi is the general wave function here. Now I don't put the t, right? Equals to h0 plus hi times psi. This is again the original Schrodinger equation we studied earlier, right? or we review at the beginning of this lecture. Which is equal to h times psi, right? That's what we need to solve, right? Now, solving this is actually pretty troublesome, but I do want you to do that. I want you to go through this troublesome because you need to do this once in a lifetime, okay? So how do we solve it? The first thing is I know that what is psi, right? From the last slide, psi equal to C0. Now I make it clear. This depends on the time. This C0 times 0 e to the power negative I omega L divided by 2t plus C1 as a function of time 1 e to the power I omega L divided by 2t. Okay, so when I apply this to here on the left hand side, or instead of left hand side, just apply directly, right? So apply the differentiation to here. So first I will get I h bar. I just take the whole thing out. First, C0 is going to get dC0. Dot means dC0 dt, right? dC0 dt. So if I do this, and then now I don't write the t to save the area, the space, right? And then I will get this one, right? Omega L divided by 2t, right? So I do a differentiate on this term, I get dot C0, but then I need to also differentiate this term, right? So this is C0, 0. When I do this differentiate, I get negative I omega L divided by 2, and then the whole thing omega L divided by 2, right? What I'm doing is just now after I differentiate this term, then I need to differentiate this term. Just use the rule from differentiation. So this one is e to the power something t, so this one go out, right? And similarly, I do the same thing for the C1 dot, right? And then 1, then I keep the rest. And then I will going to differentiate the next term, I omega L divided by, no t here, just omega L divided by 2, and then e to the power I omega L divided by 2. This is the left hand side. And then the right hand side is simple, right? It's just equal to H0 plus HI, the whole thing, and then multiply the whole state, C0, 0, e to the power negative I omega L divided by 2t plus C1, 1, e to the power I omega L divided by 2t, right? So let me say again, this is the Schrodinger equation. I do differentiation on psi first. This is psi, right? When I do differentiation, I differentiate each term one by one. And then here, this is time dependent. I got C0 dot, and then the rest a copy. And then I differentiate this one. I got negative I omega L divided by 2. The rest a copy. And that is the same for this term. Then the whole thing equals to the right-hand side, H0 plus HI. And then I just copy the whole term. Okay? And this is what I call the left-hand side. This is the right-hand side, right? Now, how do we solve this equation? Our goal is to find out C0, C1 and C0 and C1. Okay, so what I can do is I apply 0 to the left. Okay, so that I do a inner product, you can say inner product to this state. Apply this whole thing to this whole thing. Okay, now what happened to this? What do you get on the left hand side when you apply 0 to the left hand side? Well, the first thing is these are all scalar. So when it sees 0, 0 dot inner product 0 is going to give me 1. But 0 inner product 1 is going to give me 0. So this will be gone, right? Only this will be left over, right? So I get this one. The left hand side is I h bar C0 dot e to the power negative I omega L divided by 2t plus C, okay, maybe I just put a parenthesis, plus C0 negative I omega L divided by 2e to the power negative I omega L divided by 2t. Do you see this? That is because when I put this bra on the left, these are constant. These are not vector. These are scalar. They take out. So 0 inner product 0 is 1. That's why I get C0 and this term. Same here. 0 inner product 0 is 1. That's why I get this term. But then when I come to here, 0 inner product 1 is 0 because they're orthonormal basis, right? So this will be gone, right? This is what I left in the left-hand side. And this one must equal to the right-hand side, right? What is the right-hand side when I apply 0 to it? Now, this is pretty troublesome. So let me spend some space to discuss this. You have many cross terms, right? You have h0 to here, h0 to here, and then h1i to here and hi to here as distribution. For h0, right? Since 0 and 1 are the eigenvalue of h0. So after that, you will just get the eigenvalue, right? So if I apply this h0 to 0, I will get the eigenvalue of 0. And then I will get the eigenvalue of 1. And then this will disappear, right? For example, h0 applies to 1. I'm going to get the eigenvalue of 1, E1, 1, which is just a number. But then when I apply 0 to it, I'm going to get 0, E1, which is 0, E1 times 0, 1. So the whole thing is 0. It will be gone. This term will be gone, right? But on the other hand, the 0 term will stay there, right? 0, h0, 0 will give me E0, right? Because this will give me, maybe just spell it out, 0, E0, because it's an eigenvalue. So this is an operator matrix. This becomes a number, just a scalar, right? This will give me E0, 0, 0, which is E0. Okay, so it becomes a number, right? That is, so for this two term, right, this term will be gone. I only have this term left. Okay, so what is left here? The eigenvalue, we already say that E0 is what? It is just equal to equals to mu b 0. That is the eigenvalue of this thing, right? So as a result, so for h0, we only have, when we apply 0 to it, we only have C0 whatever left over is C0 and then mu B0, because this is the eigenvalue, times where's that? E to the power negative I omega L divided by 2t, right? So when I apply C0 to here, I will get the eigenvalue, which is mu B0, right, times this term. So that is for H0. Okay, we still have the H1 term. How about the H1 term? This is a little bit complicated. For HI, not H1, I'm sorry, for HI, right? For HI, what is left? For HI, what we are doing is that we are seeing this thing. We have two terms. We have 0, HI, 0, and 0, HI, 1. Based on symmetry, we will find that this one will be gone. But how? That is not difficult to understand. Because HI has a sigma x, right? HI is proportional to sigma x. So this is, if it's 0 is 1, 0 times 0, 1, 1, 0 times 1, 0. Try to go over the math. Sigma x is just like the log gate, right? You just do it. This becomes 1. So this is going to give me 0. On the other hand, this one will give me the will give me 1, right? Let's just check it, right? Let's check it. This is 1, 0, 0, 1, 1, 0, and then 0, 1, right? So this is 1, 0. What do you get? This one becomes 1, 0. This one gives you 1, right? And so this term will be gone. Only the 0 HI1 will left over. Okay? So I don't have enough space. So I added one more slide because I don't have enough space. But the point is, I hope you can, I try to explain very in detail, right? So I hope that you can try to write yourself to follow, right? So basically, for the second term, if you look at here, I mean, for the HI term, right? For HI term, I only have this one left over because I'm going to inner product with 0. So 0 to HI, and HI actually has the sigma x, right? HI has the sigma x, remember? Right? So only this one will be left over, and we also showed that this is just equals to, okay, and this is not accurate. I should say this is proportional. I should not say equals to, right? This is proportional, not equal to, because HI still have this whole term of B cosine omega 1t E divided by M H bar divided by 2, right? So this term is going to give me the whole thing, right? So the whole thing is actually, let me rewrite here. So 0 HI, right, on 1, try on 1, equals to what? Equals to B1 cosine omega 1t, right? And then we have sigma x, and not sigma x, and then we have x hat, right? And then the whole thing times 0 sigma x 1, right? Because this is HI. Okay? So as a result, this gives us this B1 cosine omega 1t. Okay? I'm sorry, we actually do not have the x hat because this is the field. We have x hat, but after the inner product with the magnetic moment, x hat is gone, right? So this is just this one, but then I actually missing the magnetic moment, which is what is that? EH bar divided by 2m, right? EH bar divided by 2m, right? This part comes from the magnetic moment. This comes from the magnetic field. X hat is gone. And then we have this sigma x. So this is the result of that, right? So with this, then I can equate the equation now. Now look at the first term. First on the left, I have this whole thing. Okay, on the left, I have this whole thing. So let me check against my cheat sheet so I can copy. Actually, I have plenty of space. I thought that I'm running out of space. So I should show. Yeah, so my cheat sheet is messed up, so I better just copy directly from here. Yeah, so the left hand side, this is the left hand side that we have, right? So let me copy. This is so right, I h bar times c naught dot e to the power negative I omega L divided by 2t minus I omega L divided by 2 c naught e to the power negative I omega L divided by 2t. This is the left hand side. This whole thing, okay, so what I'm copying, just copy this one. Equals to what? Equals to first, I have the H0 times this one, right? So this is C0 times E0, which is mu B0, e to the power negative I omega L divided by 2t. Okay, so this comes from here, right? 0 is gone and replaced by E0 because H0 multiplied to here, e to the power negative omega L 2t. And then the whole thing plus this H1 times this one, HI times this one, right? So this one, as we show here, is B1 cosine omega 1t e to the power h bar divided by 2m, right? And then we have a C1 and e to the power I omega L divided by 2t times C1 e to the power I omega L divided by 2t, right? Let me check if that's correct. Okay. Now, just to remind you, this one is due to the, this is due to the 0 proportional, or I can only say 0, right? 0. And this one is proportional due to the 0 HI 1. Okay, so they are coupling between these two basis states. Now we can further simplify if you realize that the so-called mu B, right? If you remember what is the Lamarck frequency. Lamarck frequency, if you go back to here, Lamarck frequency is just equal to 2 mu B divided by h bar, right? So this one is equals to, Lamarck frequency is 2 mu B divided by h bar, so it is equals to omega L times h bar divided by 2, right? This term divided by 2. Okay, let me rewrite it. H bar divided by 2, right? So now you compare this term with this term. This one go in I times I, negative 1, positive 1. And then this is just h bar omega L divided by 2 times C naught times this term. This is also C naught h bar omega L divided by 2 times the whole thing. So these two terms got cancelled. As a result, we have I h bar C naught dot e to the power negative I omega L divided by 2t equals to B1 cosine omega 1t E h bar divided by 2m C1 e to the power I omega L divided by 2t. Okay, so we will further simplify it. So it becomes I h0 dot, right? Dot means d0 c0 dt, right? We have this. H bar is going to get cancelled, right? So I have B1 cosine omega 1t times E h bar, no h bar because h bar I'm going to cancel it. Divided by 2m, and we have C1, and then we get e to the power I omega Lt because I just moved this term to here. Okay. Yeah, and maybe it's better I try to put this at the end. Okay, so this is the first equation I got. The change rate of change of C0 equal to B1 times E divided by 2m times cosine omega 1t times e to the power I omega t times C1. Do the same thing. Similarly, let's do it at homework. You just do the multiplication, the inner product of 1 on the left. You also get I C1 dot equals to B1 cosine omega 1t times e divided by 2m e to the power negative I omega Lt C0. That is the second equation. And now you can solve for C0 and C1. Once you solve for C0 and C1, you will be able to find out what is the general state. Okay, so now we are ready to solve the equation.